Hello and welcome to this episode of Math with Martinez. In today's video, in our second video in this series, we are looking at determining and analyzing the key features of reciprocal functions, such as the domain, range, symmetry, the relative maximum or minimum, the zeros, the asymptotes, and the increasing or decreasing intervals. So let's go ahead and get started here. You will recall from our last video that this form that we are seeing right here is that transformational form or standard form of a reciprocal function. And in standard form, we're able to identify very quickly our asymptotes. So when you have a function written in standard form here, when you have a reciprocal function in this form, your vertical asymptote is always going to be x equals your h value. And so if I were to go ahead and sketch that here on my coordinate plane, let me go ahead and do that for you all. Let's pick just an arbitrary value and create a little vertical asymptote. Trying to make those dashed lines really clear here for you. That is the line x equals h. And similarly, the horizontal asymptote is always the line y equals k. And that k value is maybe something like this. Horizontal line going through your y-axis, and that would be y equals k. Now here's the thing, here's the structure or the shape that your reciprocal function would take. If your a value is positive, then it would be very close to your horizontal asymptote, right? The end behavior would be approaching, your end behavior would be such that it's approaching that horizontal asymptote, and then it would kind of bend here and go downwards because it can get close to, but it can't actually touch the vertical asymptote. And then on the other side, it would pick up and bend and then go out and approach and get close to or drawn towards that horizontal asymptote, but it will not touch your vertical asymptote. And they also will not touch your horizontal asymptote. So that leads us to being able to recognize both the domain and the range for our function. See, the domain can be everything. Notice that this graph, its behavior is that it goes out forever to the left and it goes forever to the right. But there's this moment here where our asymptote is, where the graph does not occur. That, ladies and gentlemen, tells us what our domain will, I should say, not be. See, the domain for these reciprocal functions is everything except for or not including your h value. That symbol right there means not equal to. See, it's not equal to h because my graph, as you can see, where my h value is, my graph bends and goes down and approaches but does not touch at that value. And the range, similarly, is all these y values except for the y value where we have our asymptote. See, my graph goes down forever and it goes up forever, but there's this moment here, right, where there's a height that it does not touch. There's this height, and that height is where that asymptote is. That asymptote is a line that our graph approaches but does not touch or cross. So here's a big idea that I want you guys to take a moment to write down. The vertical asymptote is that vertical line, and I abbreviate vertical asymptote VA, that a graph approaches but does not meet. Let me delete that part right there. The vertical asymptote corresponds to the value that is excluded from your domain. Notice here that we said x is equal to h is our vertical asymptote, and that h value is what it is not going to have in the domain. Because if you allowed that h value right here, if you plugged in h, then what you would have is h minus h, and h minus h is 0, and we are not allowed to take a and divide it by 0. That is undefined. So that is why this value is not allowed in the domain of our function. Similarly, the horizontal asymptote is linked with the range. The horizontal asymptote is that horizontal line that a graph approaches as x approaches either positive or negative infinity. That horizontal asymptote is affecting the graph's end behavior. The horizontal impacts the range because the function will never reach this y value, and it is therefore excluded from the range. So this is where our graph is approaching as you go to infinity, but it is also the value that is excluded because it only approaches it and never actually touches it. Then last, increasing and decreasing intervals. Reciprocal functions with a positive a value will be decreasing on our interval from negative infinity to h and in union with h to infinity, where h is that excluded value from your domain. Remember, h is that excluded value from the domain. Now, if their a value instead is negative, then the function will be increasing on the interval from negative infinity to h in union with h to infinity. You can see here, this is a function that is decreasing forever. So as you read it, if you imagine yourself traveling, here we're going down, 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 picking up on the other side, going down, 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 down. I'm sorry, it looked like I crossed. Going down, down, staying above that line, but still decreasing at a microscopic level. That is true for your parent function and all functions when a is positive. But if you have a function where your function flips and instead looks like this because of the a value, then it would always be increasing. So those are some key features that are true for reciprocal function graphs. If you guys had any questions about that, please take a moment and share those now. And until next time, stay fired up, y'all.